Hi, and welcome back to Rosie's STEM. Today we're going to be talking about linear regression. We're going to be continuing the discussion that we had in the previous video about simple linear regression and extending that to more than one predictor variable. So if you haven't seen my previous simple linear regression video, I'm going to go ahead and put the link to that down below, and it'll be in the cards. I highly recommend that you look at that one before this one unless you already have a good understanding about the basics of regression and simple linear regression specifically. And at the end of that video, I mentioned that the next video was going to be about doing regression in Python. But as I got into creating that video, I realized that we really need to know more about multiple linear regression before it makes sense to do things in Python. So after this one, we will cover both simple and multiple linear regression coding in Python. So keep on the lookout for that. And also, I know it's been a while since my last upload. I apologize. I'm going to try to be a lot more consistent, but life got in the way there for a while. I did have the chance to update my background and my camera setup, so I'd love to know what you think about that down below. Let me know. And with that, let's get into the video. So like I said, we're going to be talking a little bit about multiple linear regression with Python today. And linear modeling really is a topic that I would normally spend many weeks on in my introductory data science course. So there are a lot of different aspects that we can cover in future videos. I'm thinking of making like a full series on it. So let me know what you'd like to see in the comments down below. As a recap, simple linear regression, which we talked about in the last video, refers to a regression with just one feature variable x and one response variable y. So our response variable is usually the thing that we're interested in trying to predict or understand. And our feature variable, or sometimes we'll call it our predictor, is a thing that we're using to try to predict or understand that response. So let's start with a question. This is the question that we talked about in the last video, which is what price could I set for my 3,000 square foot house? So what we were looking at is one predictor variable or feature, which was the size of the house, and one response variable, which is the price. So we're trying to use size to figure out housing price. And as a reminder, simple linear regression looks for the best fitting line through a cloud of points. So we have a cloud of points here. I do want to note that these are both continuous numeric variables, which means that they are numbers on a continuous scale, a continuous number line. So they can take on fractional values. They aren't just counting numbers like 1, 2, 3. And they are numeric, right? So these aren't things like, are you a freshman, sophomore, junior in high school? They're actually numbers with a numeric meaning. We can add them up, we can take an average. And this is important for regression. We need our outcome to be continuous and numeric for our modeling to make sense and work well. And for now, we're going to focus on cases where all of our variables are continuous and numeric, so our outcome and our predictor, just to make things a bit more simple. And in future videos, we can go over cases where that's not necessarily true. So first, when we think of lines, we normally picture a line in 2 dimensions, like the ones drawn here. So 2 dimensions means 2 measurements, right? Like price and size. However, we can do linear regression with more than just 2 measurements. And most of the time we are using more than just 2 measurements because we have a lot of data and we want to be able to use it to know something about our response. For example, if I'm trying to predict the price of a house, it'll be useful to use the square footage of the house, but it might also be useful to use other data as well, like the number of bedrooms or the number of bathrooms. So we can do a linear regression with an outcome variable and 2 predictors or 4 predictors or 10 predictors. And this is called multiple linear regression. So simple linear regression, we got 1 predictor, 1 outcome. Multiple linear regression, we have more predictors, more than 1, and still just 1 outcome. So here's an image that I generated using ChatGPT of a multiple linear regression in 3 dimensions. So this has 2 predictor variables and 1 outcome, so a total of 3 variables. And the translucent blue shape here would be our best fitting regression model. So when we're talking simple linear regression, we're talking about a regression line, right? Line in 2 dimensions. When we're talking about multiple linear regression, we're looking for a regression plane, or hyperplane is what we call it. But it's really just a linear model in multiple dimensions. So it's still linear. After 3D, it's kind of hard to picture this, so I can't really show you it in more dimensions than 3, but it gives you an idea of what would be going on here. And the important part to remember is that these things are still linear, right? As in not quadratic, not cubic, right? They follow the same like y equals mx plus b format, just with more variables. So it's not going to be y equals mx plus nx squared plus qx cubed, right? That would become nonlinear. Instead, right, remember our least squares regression line from the previous video looked like this. It was y hat equals m hat x plus b hat. Remember, those hats mean estimate. So these are estimates of our true best fitting regression line. And our linear model for a multiple linear regression would look something like this. So now we have 2 different predictors. We don't just have one x, but we have 2 x's, and we might call them x1 and x2. And each of those is going to have its own coefficient. So now instead of just having the m hat, we also have a w hat that we're going to need to estimate. So now we have y hat equals m hat x1 plus w hat x2 plus b hat, which is our intercept. So we might write it in this way, where we have an intercept, some n predictor variables, each with their own coefficient, b, is kind of a more general way of writing it, whereas the previous one, we said we explicitly have 2 predictors. This one's more general. We have some number n of predictors. So we have y hat equals b0, b sub 0, sometimes we'll call that b naught, plus the sum from I equals 1 to n of bi times xi. So here we have dropped the hats for our coefficients and intercept. Usually statisticians will use Greek letters when we need true values, and these Latin letters are like normal b's for estimates, so we don't always need that hat. We kind of know what we're talking about here, but we just kept the hat on the y. And if you've never seen one of these giant fancy looking e's before, this is the Greek capital letter sigma. So in math, we use that symbol to mean that we are adding things together. We'll say it's the sum. So that would read the sum for I equals 1 to n. So for n different things, we're going to add up their coefficient, their b, times the value of the variable, which is the x. So maybe each of these are like total square footage, bedroom size, number of bathrooms, acreage of the yard. Each variable has its own coefficient that explains its importance in predicting our y hat, which in our example is housing price. In the previous video, I explained that we find the best fitting line by finding the coefficients and intercept that minimize the total error. And we measured that total error by using residuals. Residuals are that vertical distance, the y distance, between a point and the line. And we want to find the line that has the smallest total residuals. We're still doing the same sort of thing here, we just have more coefficients to estimate, and our residuals are now the distance between a point and a plane instead of a point and a line. So if this is our plot from ChatGPT, let me see if I can write on this. Any of our points that are above the plane, right, we're gonna look at their vertical distance, this y distance, if y is our predictor, between them and the plane. The ones that are below the plane, we're gonna look at the distance this direction. Ignore my ability to write on this. So it's gonna look something like this, right? Maybe this one goes down here. It's a little hard to see in the 3 dimensions, but these are our residuals. We still have residuals, they're just in 3D space. So we can calculate an exact closed form solution for our least squares regression model. Just like we did in simple linear regression, the math just becomes more complicated, there's more things to estimate, and a lot of times we would represent things using matrices now that we have multiple variables. So if you know anything about linear algebra or matrix algebra, we will be representing things using matrices and calculating things that way. But usually at this point, it's much easier to start using computing, like in Python, than to try to do things mathematically and find a mathematical closed form solution. So in the next video, I'm going to introduce you to two different Python modules for regression, scikit-learn or sklearn and stats models. And we're gonna go through some examples as well. But I wanna thank you guys so much for watching. I hope you enjoyed the video. If you learned something, please let me know down below and give this video a like. And if there's things that you would like to see me cover in future videos, please let me know that in the comments as well. And also please hit subscribe if you haven't already. Subscribing to my channel really helps me out. And I will see you guys in the next video. Thanks.